not make this lecture exhaustive. But I want to present one final method to you. It's called Stochastic neighbor embedding. And it will be a change from the last 2 hours. Actually, it will go back in a way to these methods from the 60s. This is work by Martin and Hinton, who is a neural networks guy, and this will be important for this lecture. And welcome to 2008. So we're really pretty close to the, to the current day, and I think that as of today, this is still the best performing method. And I will start with the results. So I've rotated these slides so as to give you a few more pixels. This is the MNIST data, so digits. And down here, I've put a PCA projection. The digits are colored, but again, the algorithm is colorblind. So the algorithm just sees the original observations without the class labels, and the task is to find a good nonlinear embedding. So for PCA, if I disregard the colors, I would just see, a single homogeneous cloud. Putting in the labels by, using the colors, I see that, yeah, actually the zeros cluster together and the ones cluster together. So, it does make some sense, but it's nowhere near getting actual groups in the data. Now, this would be Salmon's nonlinear mapping, which we discussed briefly. And now here is this result of stochastic neighbor embedding. And that is pretty spectacular. Yeah? So to, of course, the colors, they do help us a little bit. You should pretend not to see them. But even so, I would argue that you see some quite distinct clusters here. And you must have done some research in this field and have plagued yourself with pictures like this to appreciate the quality of that. They've used the same data set using the isomap algorithm and local linear embedding. And actually, LLE is also usually considered a strong algorithm. But here, at least, with those parameterizations used and so on, they all do worse than this stochastic neighbor embedding. So how does that work? It's a nice example of a paper which is totally heuristic in nature, but uses some statistic lingo to make it to the journal. This is I don't mean this in a negative way. It's just that to publish in a high-class journal, you need to argue statistically, even if your method is not statistical, which is a bit of a pity, perhaps. But anyway, so in stochastic neighbor embedding, you create a matrix. Now, this will look very familiar to you. So this looks like the random walk Laplacian, the normalized Laplacian, but for one difference, namely, in this case, W is not symmetric. So in this case here, Wij is defined as, so I'm starting with a stochastic neighbor embedding, which was published, I think, in 2003, and then we'll go on to the T stochastic neighbor embedding. So and the reason it's not symmetric is here in the denominator. This is a data adaptive bandwidth. If you remember kernel density estimation, I argue that in low density regions you should really use wider kernels, and this adaptivity, you see this is element ij, but this depends only on I. So that's why wij is no longer the same as wji. On the other hand, d is defined as you would by now expect. So d is just the sum over the rows. So a diagonal matrix. So this is defined on the original high-dimensional observations. And so X are the original high-dimensional data. And now you define something similar in the low-dimensional space to which you embed. So let me write L tilde. Where this is defined just the same, except that we now use y's for the low-dimensional representation. And again, d tilde is used for normalization. Now the authors suggest by this normalization, this thing sums up to 1, and the authors hence suggest to look at that as a probability distribution and to look at that as a probability distribution and make them as similar as possible. And the canonical distance measure between probability distributions is the Kullback-Leibler distance. So the authors propose to minimize overall the coordinates in the low-dimensional space following expression. And I still need to say how to specify sigma. Data adaptive bandwidth is chosen such that 2 to the power of this thing is called a perplexity. It's sometimes used in the context of computer linguistics. And this is the design parameter, which is set to some constant. For example, this can be, so they say typical values are between 5 and 50. And in the experiments they show in the paper, they've set this value to 40. So rather than, and sigma is found iteratively by some kind of line search. And the overall effect of this is making the bandwidth, this is something like a soft k-nearest neighbors criterion. So it makes the bandwidth larger in low density areas. Yep.
And then you need L to define sigma. So how can you get?
This is the sigma from the high dimensional space. So the x are given, and I can find, here L is a deterministic function of the sigmas. And then you arrange the sigma such that this comes out. Okay, so I wrote L and not L tilde here. Okay. So now this is the target function that should be minimized, and unfortunately this looks like it's impossible to find stationary points, so you can just do gradient descent on that, and this is effectively what the authors proposed, namely to gradient descent with a large momentum term. So that was stochastic neighbor embedding. So overall, build the Laplacian in the high dimensional space, build a Laplacian in the low dimensional space, and then tweak around with the coordinates in the low dimensional space so as to make these Laplacians as similar as possible to each other. So this is overall what's happening. Now, T stochastic neighbor embedding makes two modifications to this procedure. And they look like minor modifications, but they have a huge impact. So overall, that seems to be a characteristic of this field. If you remember comparing Sammons mapping versus curvilinear component analysis, you make a small change in the formulation, and the results are really, can be drastically different in these unsupervised problems. So in this case here, they make two changes. Two big changes to the formulation, and then a few changes to how they actually optimize it. Firstly, they use a symmetric weight function instead. So we get a new Laplacian S for symmetric, which is the original Laplacian plus its transpose. And then secondly, and they make a big argument in the paper about why this is the proper thing to do, they use a kernel with heavier tail than Gaussian in the low dimensional space. And it is something to do with outliers and how much you try to fit all outliers, because if you try and fit all outliers with a Gaussian, it deteriorates your projection of the other points. So actually they use a very heavy tail, namely the student t-distribution with a single degree of freedom. So we have a new matrix T for the student t-distribution, tilde to say it's in the low-dimensional space. And again, there is no deep reason why you would use the t-distribution. The t-distribution can be looked at as an infinite sum over many Gaussian distributions with different width. But you know, I think it really is just a heuristic to use a distribution with a heavy tail here to be more insensitive to outliers. Okay, and then we have corresponding new Laplacian. And a new objective function. So this time taking the elements of this new symmetric Laplacian. Let me abbreviate this cost function by E. And from the model formulation side of view, point of view, this is it. Okay, there's your objective function. And in practice, there's the problem of how to minimize that. And it turns out that if you do calculus for a few pages, it actually has a very nice looking gradient. So the gradient of this cost function with respect to all your coordinates in the low dimensional space. So I use this to denote the element-wise product of two matrices. So whenever you can write something so nicely in matrices, it means that it implements well either in MATLAB or in this case on GPUs. And in fact, Van der Marten has published a paper in 2010 on doing that on a GPU. And given this gradient, you can now use the following update. For your gradient descent, your coordinates at time t is given by your coordinates at time t minus 1 plus magic step size times your gradient plus multiplication with a time-dependent another user parameter, a momentum term. So momentum term means when you have some kind of energy function, if you simply start a steepest gradient descent from this point, you will get stuck in this local minimum. But if you give if you think of this as a particle, if you give it some mass and endow it with a momentum, it can roll like a ball at the surface and can overcome You know, of course, you should have some friction, otherwise, you know, it's not going to converge ever. But this allows you to overcome minor energy barriers. And this momentum term is large initially to find a good region of your energy function. And then finally, the momentum term will become smaller and smaller. And beyond this hand-tuned momentum term, the authors make a few other tricks. And I mentioned this experience in neural networks because that is a similar class of problems. So you have a model that is potentially very expressive, but has very many local minima, and it's hard to find the best optima. So they've used all this experience and, you know, on the one hand, tweaked with these parameters here, but they do more than that. In particular, they initially introduce a force to compress their observations and argue that as long as all points are close by, it becomes easier for clusters to move through each other and to find the proper large-scale arrangement. And secondly, they introduce a term called exaggeration, which so they manipulate some of these. They manipulate some of their matrix elements in the early stages, making them larger than they really should be, and also explain why this actually improves convergence. So this is, you know, this is well defined. This is the energy function that's to be minimized, and then comes a whole lot of you know, prior expertise in global optimization in non-convex problems that comes into play to produce the good results that you've seen. However, the authors in their paper show very impressive results on a large number of data sets, and write that they have obtained all of these experiments with the same parameter settings. So while the procedure is non-trivial, it seems that those parameters they do suggest work well. And I have another example here. So the so-called Olivetti phase data set, different initializations by isomap, local linear embedding, SEM mapping, and then here again very nicely grouped by T stochastic neighbor embedding. If you want to have more fun with this and related algorithms, Martin has put a nice toolbox online where he has implemented all of the major algorithms, so all of the algorithms that we've discussed today and a few others. And actually, he provides lots of implementations. So for MATLAB, for R, for Python, even a GPU implementation of his more recent work. So very nice toolbox, and very nice of him to make it available. So if you Google for him, you will find that. Okay. So if we had more time, I would also have explained local linear embedding to you, which somebody else in the room has made good experiences with. So Martin has used it in a project and says that real research in his own PhD project, and says that he obtained much nicer embeddings with that than with PCA. And then these Laplacians, and we might do that at the very end of the semester, they can also be used for semi-supervised learning. So if you have partially labeled and partially unlabeled data, you can use the Laplacian to enforce smoothness of your learned predictor, not just throughout space, but especially along the manifold. And in that sense, the unlabeled samples start to really have an effect on your final prediction. You will have a chance to play with many of these concepts in the exercise that Anna has kindly prepared for you. So have fun with that, and see you next week.